Hi, welcome to this particular class, and here today we will be talking about very interesting application of microtechnology in drug screening. So, what I mean by drug screening? You see, when we let us take example of cancer, so that it is easier for us to understand. When a cancer is diagnosed, the patient has to go through chemotherapy, right. We know in general patient are given chemotherapy. Now, if there are 5 or 3 FDA approved drugs, 3 approved drugs that can be administered to a patient, which drug to pick from? Do we have any technology, or can we propose a technology? So, my question is that for a patient X, out of 3 drugs, let us say A, B, C, drug A would be effective, or B would be effective, or C would be effective. Same thing if there is a next patient, patient Y, out of 3 drugs A, B, C, which one would be effective? So, the question here arises, is that we need, or do we have a patient centric platform, that you take the sample of the cells or from the tumor of the patient, load that sample into the device, test these 3 drugs and tell which drug would be effective for that particular patient. Then the recovery of the patient would be better, rather than just giving from ABC any drug to the patient, right. So, we will be discussing today a technology which I have named as microchip for rapid drug screening. How we can design a microchip for this particular application, and can this microchip be used as a patient centric platform in case of chemotherapy. Now, it is not just limited to chemotherapy, it can be used for other therapies as well, where the drugs are involved, right. So, I will show you the device and we will see how we can design it, we will see what kind of results we can get, and we need to make sure that the results that we are getting it matches the gold standard, the results obtained from gold standard. So, we will be performing so we will be looking at the experiments that we can perform to understand the efficacy of drug, or to evaluate the efficacy of drug, right. So, let us see if you see the screen what we are talking about. We will be talking about a microchip for rapid drug screening. Now, let us take this scenario. What happens? A patient when goes to a hospital for consulting a clinician, depending on the results obtained from the gold standard, like MRI mammography. So, let us take an example of breast cancer. Okay. So, in breast cancer the patient has to go for MRI or mammography, and if the region is suspicious then the patient would be asked to go for biopsy. Biopsy is nothing but taking the tissue out from that particular region, so that we can see or we can perform further test to make sure that the patient is suffering from a cancer or it is not cancer. Alright. So, when the biopsy is performed, the tissue is out and tissue is sent to the path lab test. Tissue is sent to path lab test. Alright. Now, if a patient is diagnosed with cancer, then like we have taken example, out of 3 drugs A, B or C or NC, any one drug is given to the patient. One of this drug A, B or C is given to the patient, and then patient has to wait for about 3 to 4 months to understand whether the drug is effective or not, whether the tumor is dying or not, whether cancer is getting killed or not, and to wait for that amount of time is a wastage. So, what can be alternative technique? Alternative technique can be that you take the tumor or the tissue, a slice of the tissue that is obtained using biopsy, and you get the organoid and you use this organoid on a chip and flow different drugs, and can you flow different drugs means flow either drug A or B or C and get the results and tell the patient, okay, based on our experiment drug A, B and C that we have used, a particular drug is more effective for your case, and that will be a better approach. So, how can we design this chip, right? Of course, you can go for trypsinization, single cells and perform lot of other experiments related to biology. Our idea is not to understand in detail biology, but to understand how we can create or how we can fabricate a device that can tell a patient which drug will be better for his or her particular case. That means a device which is patient centric. Now, if we create an interdigitated electrodes, right, like this, and we place the tissue or spheroid on this interdigitated electrodes, then what we will get? We will get a impedance value, right, we will get a impedance value. Now, if I load a drug, let us say drug A or drug B or drug C, then if the drug is effective, there will be the tissue or the organoid, right, the tumor will start dying, and when it starts dying the conductivity would increase, and impedance would decrease. This is one way of doing it. This is one way of testing drugs A, B or C. Now, the difficulty with this is that the drug is in continuous contact with the tumor. This is a static platform. Let us say if I say drug with dotted points like this, right, the drug is shown by this kind of dotted points in this particular device. What we see is the drug is in continuous contact with the spheroids, but our body is not static. This is sorry, this is a static platform. Our body is not static, our body is dynamic. Thus, a static platform, to understand the efficacy of drug, to understand the performance of drug, is not a solution. So, what is a solution? The solution is to fabricate or to design and fabricate a microfluidic platform, because in microfluidic platform we can mimic the in vivo situation, and that will be a dynamic platform similar to our body, right. But the concept we got is that if we load the drug on the interdigitated electrodes with tumor, then we can see the change in impedance. That means, we can use impedance as a modality or electrical property to understand whether drug is effective or not. So, electrical property of tissue, which is our impedance, can be used to understand which drug is effective. Like I said, if a drug is effective, the tissue will die, the tumor will die, the cells will die, and thus there is a increase in conductivity and decrease in impedance. Thus, impedance can be used as a marker to understand which drug is effective or not. But the problem here was that we are using a static platform. So, now let us see how can we create a dynamic platform and how a dynamic platform will look like. Right. So, I have a chip right in my hand and I will show it to you, and this chip we are looking at we will be looking at how to design this chip today. I am holding this chip in my hand. This is the microfluidic chip. It is just a microfluidic chip, and it has a micro heater, it has an interdigitated electrodes, and it has a channel made out of PDMS. So, we will be looking at how we can create this chip that can be used to understand or can be used to rapidly screen different drugs. And as you can see, there are lot of contacts here. These contacts are for the electrodes, and if you see the another two contacts at the bottom, right, you can see another two contacts at the bottom. Then this contacts here, right here, this one, these are for heater, these contacts are for the electrodes, right. This 1 and 2, this contact are for heaters. Now, you can see further that there are lot of holes, right. There is a long channel here, you can see very long channel here, 1, 2, 3, 4, 5, 6, 7, 8, and there are shorter channels next to long channels, right. You can see here there is a shorter channel here to here, 1, next one, here to here, then here to here. So, there are long channels and there are short channels. On the back side, so in the front side only there is a heater, as you cannot see through the PDMS, I am showing it to you from the back side. Here is a heater, you can very clearly see there is a heater, and there are interdigitated electrodes. So, how can we fabricate such a sensor, how can we fabricate such a microfluidic chip, right, for rapid drug screening. All right. So, let us see the screen. If we see the screen, what we have? We have at the bottom, at the first step is your micro heater or a heater. Why we require heater? So that we can achieve 37 degree centigrade for the cells to be alive, right. So, we can keep cells alive if we can have 37 degree centigrade temperature. Now, which is similar temperature to the incubator, similar temperature to the incubator. Over this micro heater, there is a insulator. On this insulator, there are interdigitated electrodes. If I zoom in, then I can see here each electrodes has a shape which is shown here, right. So, what is the first step? First step is my heater, second step is the insulator, third step is the fabrication of interdigitated electrodes. Next step would be to fabricate or to fabricate a chip with different channels, right, and these channels we can create in PDMS. Okay. So, we will be learning how to fabricate this particular microfluidic chip, and if you see the chip, what you see here is, see, there is a drug inlet, there is, see, I will just draw it here. this one is your longer channel, right. This one is your shorter channel, small channel, shorter channel, right. So, just consider 1, then there are similarly there are 8, 1 to 8, alright. So, what we are discussing here? We are discussing only one channel, which is a longer channel and a shorter channel. So, longer channel, we have to load the drug from here, we have to take out the drug from here. We will load the drug from one end, we will take out the drug from another end. This is what it is written here, drug inlets and drug outlets. Okay. Now, if you consider the shorter channel, we load the cancer cell, we load here in the shorter channel, we load cancer cells. You can also load spheroids, you can also load organoids, right, like a tumor, cancer cells with matrigel. What is matrigel? Any cancer, when we see a cancer, is always surrounded by ECM, extracellular matrix. Any cancer is surrounded by extracellular matrix. This extracellular matrix we can replicate by using matrigel. Thus, cancer cells are mixed with matrigel, you can see here, right, and can be loaded into the shorter channel. So, cancer cells with matrigel, right, are loaded into the shorter channel here. Now, if I enlarge this particular channel, then it is like this. Okay. And below this channel, there is this interdigitated electrodes. Which one? The one which is here, right. Below this channel there is interdigitated electrodes. Below interdigitated electrodes there is an insulator, and below insulator there is a heater. You got it? So, first layer is your heater, second layer is your insulator, third layer is your interdigitated electrodes, and fourth layer would be your channels made out of PDMS. So, let us now see how we can fabricate the device, and we will discuss in detail how this device can be used for rapid drug screening. Right. The electrodes, for sure, this are used for impedance measurement, which is given here. The heater contact pairs that we have just seen, I have shown you the device, and the contact pairs are used to apply power, so that the heater can achieve 37 degrees centigrade temperature. Right. So, let us see one by one. First step is we have to fabricate a micro heater. Right. So, how can we fabricate a micro heater? Now, everything is on glass, right. So, we take a glass, and we deposit a metal for micro heater. Let us say my metal is nichrome, right. So, I have deposited a metal which is nichrome for my heater. What is the next step? My next step would be I will spin coat photoresist, right. You see, I have spin coated photoresist. Which one? Positive photoresist, right. This is first step. You can always say that I take a glass, the glass substrate, I can consider this as first step to take a glass substrate, right, and make it ready by cleaning it for the fabrication. Second step can be depositing nichrome for heater. Third step can be positive photoresist, spin coating positive photoresist on the metal coated glass. Next step after positive photoresist, this is photoresist, this is my nichrome and this is my glass, right. Next step, which is my fourth step would be to load the mask, right. I have to load the mask so that I can perform photolithography, correct. So, I am loading a bright field mask. What kind of mask I am loading? Bright field mask. Now, what kind of photoresist I have? Positive photoresist. Positive photoresist. So, if I expose this mask, expose this whole glass wafer, right, along with mask and positive photoresist with UV, what will happen? The area which is not exposed. So, which one? This one which is bold, like this. So, the area which are not exposed will be stronger and the area which are exposed would be weaker. So, fourth step would be to load the mask and perform UV exposure. Fifth step would be to develop the glass, develop the photoresist, and when we want to develop the photoresist, what we get? We have nichrome, right, and we have photoresist. So, I will get this kind of pattern, correct. What is next step? Next step would be to etch. No, are we missing something? You see, after positive photoresist, what is the step? Soft bake, right? Soft bake, then UV exposure. After UV exposure, photoresist developer. When you perform photoresist developer, then photoresist will get developed. This is your photoresist, this is your nichrome, this is your glass, right. After this would be hard bake. Hard bake is done at 120 degree centigrade for 1 minute, right. When you perform hard bake, then next step would be to etch nichrome, right. So, when we etch nichrome, the area which is protected by photoresist will not get etched and the area which is not protected by photoresist will get etched. So, what we will have? We will have a glass wafer with micro heater, nichrome, glass, correct. So, I have now designed a process flow for fabricating a micro heater. First step done, excellent. What is the next step? Next step is to form interdigitated electrodes, but before forming interdigitated electrodes, I have to cover my nichrome with an insulator, because we cannot have metal over metal, it will be shorted, right. So, before I go for interdigitated electrodes, what I have? I have a glass wafer with micro heater, right. This is what I have. My next step would be I will grow silicon dioxide onto this micro heater, correct, and I will perform photolithography to remove the silicon dioxide from the contact pads. You see, you do not want silicon dioxide on the contact pads, right. You do not need it, because otherwise if there is silicon dioxide on contact pad, you cannot apply any voltage, it is an insulator. So, you have to perform photolithography such that the silicon dioxide from the contact pad is removed, is etched. Okay. So, now I am hoping that you know how to perform photolithography. So, I am just skipping that step. What I am doing is I have taken a glass with micro heater, on that micro heater we have grown silicon dioxide, and then you perform photolithography such that the silicon dioxide from the contact area of the micro heater is etched. Here the silicon dioxide should be etched. So, if I now see a wafer, right, if I now see the wafer, how it will look like? You see, it will look like this. Assume that this is a thick, everywhere there is a silicon dioxide, right, everywhere there is silicon dioxide except right, except this area. Or in another way, if I want to draw, I will just draw like this. So, you can understand, right. Assume that everywhere it is silicon dioxide, everywhere silicon dioxide is there, all right, everywhere silicon dioxide is there. Except contact pads, except contact pads like this. Right, everywhere there is silicon dioxide. Like this, silicon dioxide. So, heater is covered with silicon dioxide, heater is covered with silicon dioxide, right, about 1 micron silicon dioxide we can grow using PECVD, plasma enhanced chemical vapor deposition, right. What you can see, only heater, the silicon dioxide from heater contact pads of the heater is out. So, once you do this, once you deposit or you grow silicon dioxide and you perform photolithography such that the silicon dioxide is etched from the contact pad, the next step would be to fabricate interdigitated electrodes. So, let us see how we can fabricate interdigitated electrodes. So, once I have this, assuming that I have taken out the silicon dioxide, I have etched silicon dioxide from the contact pads, my next step would be to deposit metal for interdigitated electrodes. So, let us say I have chrome gold as an interdigitated electrodes, right. How can I deposit this metal? You can deposit either by E beam or sputtering, E beam or sputtering. What is the next step? My next step would be to start photolithography process, right, to start photolithography process. So, what is photolithography process? I have chrome gold, right, I have a insulating layer and I have a micro heater. Correct. On this I will deposit, or not a deposit, I will spin coat photoresist, chrome gold, silicon dioxide, nichrome, glass, right. On this, what is the next step? After this we have to pre-bake at 90 degree centigrade. Next step would be to load the mask, correct. So, I am loading the mask, I am loading a bright field mask, right. I am loading a bright field mask for creating interdigitated electrodes. this is my bright field mask. Okay. Now, next step would be UV exposure. Next step would be PR developer, right. So, after I perform UV exposure and PR developer, what will I have? I will have chrome gold, silicon dioxide, glass, nichrome and photoresist developed, right. Now, the area which were exposed, the areas which were exposed with UV were weaker, the areas which were not exposed got stronger, because we use positive photoresist. We use positive photoresist, right, positive photoresist. Now, what is the next step? Next step would be etch chrome gold. When you etch chrome and gold, you know how to etch chrome and gold. First you have to etch gold and then chrome, because chrome is at the bottom, gold is at the top. When you etch chrome gold, the area which is protected by the photoresist will be saved, it will not get etched, and the areas which are not protected by photoresist will get etched. So, what you will have? You will have a wafer, a glass substrate, right, a glass substrate, with interdigitated electrodes at the top, SiO2 next to it, at the bottom there is a heater and the substrate is your glass. You got it? This is what you got. Now, what you have? A heater at the bottom, insulator in between your electrodes and the heater. Good. What is the next step? Next step is we have to create channels, right. We have to create channels. This is super easy. Okay. There are two ways. I will show you one way today, and then sometime in the next modules I will show you the another way of creating these channels, right. Today we will be learning the creation of these channels by using a mold that is fabricated using SU8. Okay. And then next time we will see how we can create a mold to create this channel using DRI, that is by etching silicon itself. So, let us see how we can fabricate this particular channels and how we can use the mold. So, for that you have to take silicon, oxidized silicon, right, that is oxidized silicon. SiO2, On this you spin coat SU8. What do you do? You spin coat SU8, alright. SU8 is which kind of photoresist? SU8 is negative, it shows property similar to negative photoresist. Okay. Now, what we want to do? We have to create this channel, right. After you spin coat SU8, you have to pre-bake it. Now, for SU8 the pre-bake temperature is somewhere around 65 degrees centigrade, and depending on the thickness of SU8 the time also varies, right. For positive photoresist and negative photoresist, what we are discussing? We were discussing till now that the soft bake temperature or pre bake temperature is 90 degree centigrade, and if you use hot plate, then you can heat it for or bake it for 1 minute. The post bake temperature was 120 degree centigrade. Again, if you are using hot plate, you can bake it for 1 minute. This is for positive and negative photoresist, right. But for SU8, 65 degree is your soft bake. The time depends on thickness of SU8, all right. That is the first step that you have to understand. Second step is, second most important point in while using SU8 is that in our photolithography process, standard photolithography, the steps are like this: spin coat photoresist, next step would be soft bake, 91 minute, next step would be mask align and UV exposure, right. Next step would be PR developer, next step would be hard bake, 120 degree centigrade, again 1 minute on hot plate. This is our standard lithography process, right. But when you want to use this for positive and negative photoresist, when you want to use SU8, first step is PR. So, SU8 spin coat, SU8 is similar to negative photoresist, but anyway SU8 spin coat. Next step would be soft bake, temperature is different, time is different. I told you time depends on the thickness, Next step would be mask align and UV exposure. Next step is hard bake, 95 degree centigrade for some time, depends on thickness. Then comes PR developing. Where is the difference? That in SU8, after soft bake and mask aligning, there is a hard bake before we go for photoresist developer, while in normal standard photolithography, once you have soft bake, mask aligner, there is a PR developer and then there is a hard bake. You see here, after mask aligner, there is a hard bake and then there is a PR, right. This is the only difference. The advantage of using SU8 is that SU8 is obtained or we can get SU8 of different viscosity, and thus the thickness of the channel can be different. The SU8 is easy, first of all, because just photoresist that we have to pattern. Second is that the thickness can be varied depending on the type of SU8 that we are using. There are several types of SU8, SU8 25, SU8 50 and lot of other SU8 depending on the thickness that we want, all right. So, here what we have done, we have taken oxidized silicon wafer, we have spin coated SU8. Next step would be pre bake, right. If I go here, next step is my soft bake, let us write soft bake. Next step would be exposure, right. So, I will just draw wafer, silicon dioxide. So, it is a oxidized silicon wafer, right, on which there is a SU8. on which there should be the mask, right, there should be mask. Now, you have to be careful because SU8 acts as a negative photoresist, okay, acts as negative photoresist. So, what you want now? You want to create a hills. So, the area which is exposed will be stronger and the area which is not exposed will get weaker. The area which is not exposed, because that is a property of a negative photoresist, correct. So, what we can do? We can use bright field mask, we can alternative use dark field mask, such that we can have a pattern that looks like the one I am drawing here. Okay. And somewhere on the back side there are another pattern. So, this is a cross sectional view. So, you should understand this is SU8, SiO2, silicon, SiO2 here. So, to obtain this one we have to use mask, which is shown here. After mask, what is the next step? Next step would be exposure, UV exposure. When you perform UV exposure, next step would be hard bake, not developer, okay, hard bake. After hard bake, which is an 95 degree centigrade for particular time depending on the thickness of SU8, next step would be sorry, this is entire mask is like this, entire mask is like this. Right. So, next step would be hard bake, and then we have to develop photoresist. When you develop photoresist, you will obtain this particular mold. Now, what you will do with this mold? What you will do with this mold, right? So, with this mold, right, SU8 mold, what we will do? We will pour PDMS and cure it, pour PDMS and cure it. When you pour PDMS and cure it at 115 degree centigrade for 15 minutes, then you can peel this PDMS off. If you peel the PDMS, what you will get is let me just redraw it. This channels, right, because there was SU8, this is PDMS. When you pour the PDMS and cure it, and when you peel it off, you will have PDMS as shown in schematic, this one. Okay. Now, what you have? you have a glass wafer with heater, right, and interdigitated electrodes, right. And you have PDMS. So, this is 1 and this is 2, correct. These 2 things you have. So, let me just rub this down. Now, we know that how you can create PDMS, right. So, what we have? We have wafer 1 with interdigitated electrodes SiO2, this is chrome gold, interdigitated electrodes which are this one, right. Then we have silicon dioxide, then we have micro heater which is this one, right, and we have PDMS, correct. This is my second wafer. 1, 2, right. Now, what I will do is I will perform oxygen plasma technique, and after performing oxygen plasma technique I will stick PDMS to the glass. So, after performing oxygen plasma technique, this is done at 100 watts, right, for particular pressure of nitrogen or argon. Is it correct? No, right. Initially nitrogen can be used, but then we require oxygen, right. So, 100 watt of power and about 10 millitorr of oxygen. Okay. So, we can there is a generation of plasma that will create a surface, that is functionalize the surface, so that it is ready for bonding. Next step would be next step would be I have a glass wafer, I have a micro heater, I have interdigitated electrodes on which I am loading this substrate, right. I am loading this substrate. So, what will I have? I will have like this, something like this, correct. I will have a feature which is like this, because now you see if I draw this with let us say 0 pattern, then you see here where is my PDMS? My PDMS is here, and thus I have a channel. You can see a channel, right. You can see this channel and you can see this channel. So, what I have done is I have sticked PDMS onto the glass substrate which is integrated with a micro heater and interdigital electrodes and separated by a silicon dioxide or an insulator. So, once I have this device, what is the use? I cannot operate anything. So, before you stick like this, before you go for oxygen plasma, you have to create a hole in the PDMS. You have to create a hole in the PDMS, so that you can use for loading or flowing the drugs and loading cancer cells, right. In the shorter channels, you are loading cancer cells. In the longer channels, you are flowing drugs. But how can you load if you do not have the inlet and outlet? So, to create inlet and outlet, you have to create holes in PDMS. You have to create holes in PDMS, something like this. Right, there is a hole, How can you create a hole? By using acupunch, by using a biopsy needle you can create a hole in the PDMS. Alright. If you have this, then it is easy to connect the inlet and outlet or to load the drug. Alright. So, what we have seen, how can we have micro heater and how can what is the process flow for micro heater? On that there is an insulator, on that there are interdigital electrodes over which there are PDMS channels, and we are sticking all together to get a microchip. Now, the question is, once you develop this microchip, how can you use for rapid drug screening? Right. Once we now know what is the process for fabricating this microchip. So, what is the next step so that we can use this microchip for rapid drug screening? So, we will see this in the next class, in the next module of this particular lecture, and we will see what kind of data we can generate using what kind of drugs, right. So, there are different drugs, different cells. We will see the data obtained from melanoma, which is skin cancer, from prostate cancer cells, and from breast cancer cells. And we will see two different kind of drugs, one is paclitaxel, another one is carboplatin, right, platinum based drugs or taxol based drugs. So, when we use platinum based drugs, when we use taxol based drugs, what kind of results, what kind of electrical properties we can find out depending on the efficacy of the drug. So, we will see in the next module. Till then you take care, I will see you in next class. Bye.